Hello everyone. In this video, we're going to chapter 16. We're going to cover 16.1 through 16.3 today. In this section, we're going to look at kinematics of a rigid body undergoing planar translation or rotation about a fixed axis. Let me show you some diagrams. It makes better sense once you see the diagrams. There are cases where object cannot be treated as particle. So you know that things that we deal with all the time, they always have size, well, has shape. And then sometimes, and a lot of times, we do need to consider the size and the shapes of the body. Rotation of the body about its center of mass requires a different approach. For example, in the design of gears, links in machinery, rotation of the body is an important aspect of the analysis of the motion. We will start now to study rigid body motion. The analysis will be limited to planar motion. And again, I will show you a lot of diagrams. A body is said to undergo planar motion when all parts of the body move along paths from a fixed plane. So the first diagram here, we're going to look at three different planar rigid body motion. First diagram right here, we call it regular linear translation. So in other words, we're moving on a straight line. Second diagram, this one right here, second one, I'm referring to the upper right corner. The path, we called it, this is a curvilinear translation. Number 3, lower left corner, is rotating about a fixed axis, pretty straightforward. And the last one is a general plane motion, meaning I'm having a combination of translational motion and the rotational motion. Take a look at how do we define it in words. Translational motion means that if every line segment on the body remains parallel to its original direction during the motion. When all points move along straight lines, the motion is called regular linear translation. And then when the path of motion are curved lines, the motion is called curvilinear translation. So both of them are translation, but one is regular linear translation. Excuse me. The second one is curvilinear translation. If I'm rotating about a fixed axis, in this case, all the particles of the body, except these on the axis of rotation, move along circular path in planes perpendicular to the axis of rotation. General plane motion, in this case, will be a combination of translation motion and rotational motion. Translation occurs within a plane and rotation occurs about an axis perpendicular to this plane. So here's an example. I have the piston here on the left that is going to go left and right, left and right. Okay, so the piston is regular linear translational motion only. And then if you look at the right side of this machine, this thing right here is going to be rotational motion, right? It's rotating about center of rotation, this right here, rotating about that point, left and right, left and right. Okay, and the connecting rod undergoes curvilinear translation. Now, connecting rod undergoes, so that means connecting this rod that's connecting them together is a combination of translating and rotating. So this one right here, this rod right here, translating and rotating at the same time. Okay, we call that the general plane motion. So it's both translating and rotating. Next definition that we're going to look at is relative position, absolute position, relative position, and acceleration as well. So the position of 2 points A and B on the translating body can be related as RA equals RB, RB equals RA plus RB/A. So over here, RA and RB and B/A, they're all vectors. This is vector addition. Now RA and RB here refers to the absolute position vector defined from the fixed xy coordinate system, and rb/a is the relative position vector between b and a. The velocity at b will be vb equals va plus derivative of rb/a, relative position of b with respect to a, taking that position vector first derivative with respect to time. And then now d rb/a over dt, so first derivative of position rb with respect to a with respect to time equal to 0, since rb/a is a constant. So that means velocity a and b equal to each other. And following by the same logic, that means the acceleration equal to each other as well. Now, all points in the rigid body are subject to translation motion, translation move with the same velocity and acceleration. Let's take a look at rotational motion. When a body rotates about a fixed axis, any point P in the body travels along a circular path. The angular position of P is defined by theta. The change in angular position d theta is called the angular displacement. With units either radians or revolution, we know there's a small unit conversion here. Every one turn, every one revolution is equivalent to 2 pi of a radius. Angular velocity omega is obtained by taking the time derivative of angular displacement. So omega equals d theta dt, derivative of theta with respect to time. We have the unit of radians per second. Similarly, angular acceleration is going to be the relative position vector with respect acceleration. Angular acceleration is theta second derivative with respect to time. Okay, so d theta squared over dt squared, or angular velocity with first derivative of angular velocity with respect to time. So similar to what we learned before, but except everything in here we talk about angular. Linear velocity becomes angular velocity, linear acceleration becomes angular acceleration. And the rest of the concept is all the same because we are rotating. If the angular acceleration of the body is constant, so I have a equals alpha, not a alpha, that refers to angular acceleration, alpha equals alpha c. The equations for angular velocity and acceleration can be integrated to yield the set of algebraic equations shown below. Notice that these three sets of master equation is very similar to the linear ones that we've seen before, okay, except they are for angular. So we have omega and theta instead of velocity v and s, and then acceleration will be a. Now in here, all the acceleration is alpha, which all of these refers to angular movements. Theta 0 and omega 0 are the initial values of the body's angular position, angular velocity. And note that these equations are very similar to the constant acceleration relations developed from regular linear motion of a particle. Magnitude of the velocity p is equal to omega times r. So in other words, whenever we're relating linear velocity to angular velocity, they are one radius away. So taking the angular velocity times radius, that gives me the linear velocity. Same thing as acceleration. Angular acceleration multiplied by the radius gives me the linear acceleration. So the vector formulation, the magnitude and direction of v can be determined from the cross product of omega and rp, where rp is the vector from any point on the axis of rotation to p. So velocity over here, remember we say from linear to angular, they are one radius away, right? You multiply by the radius. So over here, v equals r cross r times rp, omega times rp, or omega times r. Direction of the velocity is determined by the right-hand rule. The acceleration of p is expressed in terms of its normal and tangent. So normal form an, tangent form at. In the scalar form, we have at equals, on the tangent component will be alpha times r, see, only one radius away. And then the normal component will be omega squared over r, okay? Tangent component at represents the time rate of change in the velocity's magnitude. Tangent component changes the magnitude. It's directly tangent to the path of motion. And then if it's normal component changes the direction. AN changes direction. And then the one changes direction always directly toward the center of the circular path. Similar to the linear equation that we seen. So over here, A equals dv dt. That will be d omega over dt times rp plus omega drp over dt. So in other words, I have the tangent component of the acceleration plus the normal component of the acceleration. Okay, it can be shown that in this equation, reduce A equals alpha times r minus omega squared times r. So a tangent, a normal together. And again, they are all vectors. If you're looking for the overall magnitude of the acceleration, you do Pythagorean theorem. And we're going to establish this sign convention along the axis of rotation. If a relationship is known between any two of the variables, alpha, omega, theta, or t, the other variables can be determined from the equations. Omega equals dv d theta dt, alpha equals d omega dt, alpha d theta equals omega d omega. Under the condition that alpha is constant, we have constant angular acceleration. We're going to use the equation for constant angular acceleration to determine the motion of motion of a point. Scalar equation, we have v equals omega r, at equals omega alpha r, and then an normal acceleration normal will be omega squared times r. And then alternatively, in the vector form equation, we have the ijk component. Okay, so you will relating these equations for the vector form. Now let's take a look at some examples. We have three gears put together. Okay, what I want you to do is take a look at this picture, this diagram here. Gear A and gear B, they are in contact point right here in the middle. Gear A and gear B in contact. That means A and B share the same linear velocity. Their linear velocity or linear acceleration will always be the same, A and B, because they are in contact. Okay. If I'm what? That's ugly. Let me try it again. A and B in contact, gear A, gear B, they have the same linear velocity and linear acceleration. For gear, let me use a different color. Gear B and D, they are on top of each other. One is on top of the other one. Gear B and gear D, they share the same angular velocity and angular acceleration. Okay? Because they're on top of they're rotating together. That means they rotate the same angle together. The linear velocity B and D linear velocity will not be the same because one of them's got a bigger radius, the other one's got a smaller radius, but they share the same center. They're on top of each other. They share the same angular velocity and the same angular acceleration. With that in mind, we're going to take a look at what's going on. We're looking for cylinder C, right? Cylinder C right here, we're looking for the velocity of C and distance when it travels 3 seconds. So in other words, the point C over here, all we got to know is figure out what's going on with the C, right? We need the velocity and acceleration of C, which will be the velocity and acceleration of this gear D because it's in contact with D. Okay, so what we're looking for is the um, linear velocity, linear acceleration of gear D. Okay, so being said, when we say A and B share the same tangent component, they have the same acceleration tangent. Okay, alpha A RA, alpha B RB is the same thing because they share the same linear velocity and same linear acceleration. With that in mind, plugging our value, we can get the angular velocity of B. Okay, if you need the diagram, refer back to the diagram. Okay, from A, we get to B. We understand we get our angular acceleration to B. Angular acceleration B and angular acceleration of D. Remember, we say B and D angular are the same. Angular acceleration to B and angular acceleration of D are the same thing. And with that, we can calculate the we can use this alpha d rd to calculate the the linear, the tangent alpha drd gives me the tangent acceleration of d, which is the same the tangent acceleration of c, which is what we're looking for. Okay, hope you find the relationship just fine. Once we got the d, linear acceleration, linear velocity of c and d are the same thing. Okay, now with that, we know 3 seconds, right? 3 seconds, we know the initial velocity, we know the which initial velocity is 0, right? We plug in the acceleration that we just found in time to get the linear velocity at 3 seconds. And then sc, the total distance over here, we know the ac, linear acceleration of c, then plug in, since the first two terms are 0, 1/2 acceleration times t squared. That gives me the total distance that will travel. This unit, I kind of disagree. This unit should be meters, not meters per second, because we're calculating the distance to travel. All right, next problem, very similar. I feel like this one's slightly, actually a little more, slightly simpler. We have two gears, gear A and gear B. Since they're in contact, we know that A and B share the same linear velocity and linear acceleration. Okay, alpha A is given to us. Okay, it's a function of time. Omega A initial, this is only the initial acceleration of a angular acceleration of a changes, right? So from alpha A we can take the integral to get the omega. Okay, we're taking the integral of angular velocity, that gives me the, sorry, taking the integral of angular acceleration, that will give me the angular velocity, function of angular velocity. And then if we take the integral of angular velocity, that will give me the position. So how the function of position with respect to time. Plug in 2 seconds. We're looking for 2 seconds later, what's the angular velocity and acceleration, right? Since we get the equation, we get a function. Plug in 2 seconds, we get the angular velocity and the angular position. Angular, so angular distance, how much angular distance to travel, how much radius. Okay, and also since B and A share the contact, they're in contact, right? That means their angular acceleration is the same. With omega A RA equals omega B RB, we can calculate. We have this relationship. We know how omega A, angular velocity of A, and angular velocity B, we know their ratio of each other. Similarly, how much radiance, how much distance they travel angularly, angular distance that they travel is in ratio as well. And then we'll plug in the 2 seconds. That will give us the angular velocity and the angular distance that they travel. Again, I believe the per second should not be there. That should be radians only. Okay, that's all I want to share with you in this video. Hope you find